Hello and welcome back to Symmetries and Quantum Mechanics. In the last lecture we started exploring the consequences of Shor's lemma, and one of them is this remarkable corollary. This corollary will be the main tool we use to extract irreducible representations as sub-representations of bigger representations. As a reminder, what does this corollary say? It says if you have a linear map between two irreducible representations, V1 and V2, then you might hope that H is somehow a intertwiner in the sense that I described in one of the previous lectures. But it probably isn't, right? It's probably not covariant with respect to the action of the group. So what you do is you take this linear map and you do this averaging trick that I introduced several lectures ago, and that produces for you a different linear map. H0 is linear, it's a map, and it goes between V1 to V2, but this one is covariant with respect to the action of the group, meaning if you do if you act on the right with an element of the group, then that's equal to acting on the left with the corresponding representation on the other side. So that's the averaging trick applied to any linear map. It doesn't matter, any linear map, just think of one. And then immediately we're now in a setting where you can basically just directly apply Shor's lemma. Either these two representations are non-isomorphic, they're different representations, and then the only choice possible for H0 is just 0. Just always averages out to 0. That's part of Shor's lemma. Or the representations are isomorphic, in which case then the map can be non-trivial, but the only way it can be non-trivial is if it's the identity map. The only thing that commutes with every element of the group, according to this representation, if it's the same representation, is the identity map. And there's a scale factor here, 1 over h trace of h, 1 over n, oopsies, 1 over n trace of h times by the identity. N is the dimension of this representation here. So that was this corollary. This corollary is Shor's lemma in disguise or applied to this averaged version of h. And kind of surprisingly, this leads to quite a few dramatic consequences. So I invited you in the last lecture to think about this in terms of matrices. So this equation for H0, if you think of H, H, I invited you to think of H as a kind of rectangular matrix, right? H is going between V1 and V2. V1 might be bigger than V2, or V1 might be smaller than V2. I've drawn the rectangle this way, but could have done it another way. And we have these matrices here. This is row T1, this is row T2, and we're summing over the group, 1 over the number of elements in the group, and that builds for us a rectangular matrix that we call H0. Right, so that's what I invited you to think about last time. Should make it a bit smaller. Now, what are the matrix elements of these things? I'm just going to write the matrix elements of these as R, J, K, T. And the matrix elements, and that's a 1 here, 2 here. And the matrix elements of this thing is R, J, K, T, 1. And I'll put primes there to indicate that the matrix elements and these matrices are different than these matrices here. And then we've got two matrices here. We've got a matrix H. Well, its matrix elements we'll just write as X, J, K. And we've got a matrix equation, right? So let's ask ourselves, what things are we free, or what things do we know, and then what things are we free to choose? So one thing we know is if V1 is not equal to V2, we know something, right? We know that no matter what we put in here, no matter what numbers we choose for the matrix elements of H, it's always 0 in here. So let's do this case first. So there's nothing there. It's all zeros. So for all elements x, j, k that you can possibly put in there, the right-hand side is always 0. And there's a convenient choice of xj entries that you can put in there. You could put in the matrix, which is zeros everywhere except a 1 somewhere. So let's do that. You know, 0, if j is not equal to special j1 and k is not equal to special k1, and 1 if j is equal to j1 and k is equal to k1, the special one. So we've got, you know, dimension of v1 times by dimension of v2 choices of where we can put that number 1. So we could put the number 1 here in the first entry, we could put the number 1 in the second entry, and so on. So we've got lots and lots of freedom to put a number 1 in here. And each time we do that, we get the number 0. We get a matrix of zeros out. So this gives us dimension of v1 times by dimension of v2 choices for where, you know, 1 appears. And each time we make one of those choices, we have dimension of v1 times dimension of v2 equations here. And in the case where these are square matrices, it's basically the same, except now the matrix is got 1s on the diagonals on the left-hand side. And the representations are now the same size. There should be an inverse there. Same story. I could put a number 1 anywhere I want in here. And I get loads of equations. And let's think about putting a number 1, say, in this first entry here. If I put a number 1 in here, then when I multiply these 3 matrices, let's imagine what comes out if I put in a 1 there. So if I put in a 1 here, say, then all the rows of this product here are 0 except for the first one. And then all the columns of this one are 0 except for the first one. So actually only one number comes out of this entire product if I put a 1 in that first place there. And that number is, well, I have to write it out. Let's choose j1 equals k1 equals 1, you know, according to this scheme here. What do we get when we multiply those 3 matrices together? We get R T 1 M R inverse or RT inverse L1 sum over T 1 over G. So that's the equation we get, and that's got to equal 0 for all L and M. We get a matrix out at the end. That's the rows of this matrix we get out at the end. There's the columns of the matrix we get out at the end. Actually, we learn lots and lots of equations about these entries here. I'm not going to write out the second. I'm just going to summarize now these results. So the result of all this discussion is a simple summary, and that tells us, that summarizes the behavior of this equation, but written in terms of matrix elements. I'm just going to write everything in terms of matrix elements, and that turns out to be a bit more useful. So I've already effectively proved this corollary with this discussion. Okay, so in the case where V1 is not equal to V2, we learn that all these matrix elements, oh, I got it wrong way around. It doesn't matter, but let's just do it the correct way around. All these matrix elements are 0 once you sum them over the elements of the group. And then in the other case, same argument. I'll just do it with 2's here. Okay, there we go. 2 simple little consequences of this matrix equation up there. Now, I invited you in the last lecture to think of these matrix elements as a function on the group. So the argument is T, the element of the group. And each one of these matrix elements of an irreducible representation, you think of them as a function on the group. And that way they live in a Hilbert space when we have a unitary representation. And we're going to use that pretty much going forward. They live in the Hilbert space of all square integrable functions on the group. So the matrix elements of a representation, you think of them as themselves as functions on the group. And these innocuous corollaries here tell us tremendous amount of information about these functions. In particular, it tells us that those functions form you can think of these functions as vectors also. I'll write down that interpretation in a second. And this gives you a whole bunch of orthogonality relations for these vectors. So in fact, what this lemma gives us is it gives us a full orthonormal basis for the functions on the group itself, for L2G. All right, so you think of this as a function on the group. Also, as a vector, you think of it also as a vector on the group with entries. So RJK, the identity, RJK, first element of the group, which we'll call G1, RJK, second element of the group, and so on. Right? A function on the group itself is just an assignment of a complex number to each element of the group. But I could line up all those complex numbers in a vector. How many of them are there? Well, there's G of them. G equals the order of the group entries. So I know there's this JK here. Try and imagine that JK isn't there. Just try to imagine you've got this list of complex numbers without the JK. So you can either think of this matrix element as a function on the group or as a vector with exactly G elements. And then we can look at this thing up here, and we're going to start to learn some interesting things about these equations there. There's lots of equations there. And they say that lots of things are 0, which should be a surprise, right? In physics, when something is 0, then there's usually a symmetry principle why it is 0, right? Whenever you see an equation equals 0, there has to be an explanation why. Generically, things aren't 0. If I take random numbers and add them together, I don't get 0, right? Generically, I get some number. So if you take a bunch of numbers, namely these RJKs, and you multiply them like that, and they're getting 0, then there must be a deep explanation why. Because if I had taken random RJKs, these entries were just random numbers and I computed that product right there, I wouldn't get 0. With probability 1, I'd always get a number not equal to 0. So this tells us these numbers are special. There's a deeper principle that these numbers should obey these equations here. Always true. Whenever you have a list of numbers that obey an equation, look for a deeper principle. Because if you replace those numbers with random numbers and you don't get that equation being obeyed, then you can see that there's structure there. All right, we're going to think of these things as functions on the group itself, also as a vector. So I like to think of them as quantum states on the group. So I like to think of each of these vectors, for every choice of jk, as a quantum state of a quantum particle that's moving on this group. So the group is kind of like the position space, and the particle is allowed to be, it's allowed to get into superposition over this group, and one of these functions is just one of these quantum states. Now, moving forward, we're going to assume that our irreps are unitary. You can phrase everything a bit more generally. In Serre's book, he keeps it always, these two cases, he does the non-unitary case and the unitary case kind of in parallel. But if we keep doing that for much longer, we're going to have a horrible set of notations to do with scalar products. I want to avoid that as much as I can in this course. It's a quantum mechanics course after all, so we're going to now specialize all our results to the unitary case to avoid having to introduce 2-3 sets of scalar products. It's not worth the pain. So let's assume that our irreps are unitary. What does that mean? It means if you have one of these matrices that does that element of the group, and then you take the dagger of it, well, you're going to get the inverse like that. Or otherwise said, RJKT complex conjugate is RKJT inverse. I think. Bet I messed that up. Did you mess that up? No, it's correct. It's correct. So these are the matrix elements of these operators here. Good. So let's assume that our irreps are unitary. And now we're going to reinterpret these things, these statements here, and we're going to learn that these entries obey some pretty amazing properties. So we're going to do so by introducing a scalar product. So I said, let's make these things an element of group, this Hilbert space here, but I never told you what the scalar product is. It's all very well to talk about a Hilbert space like L2G, but I have to tell you what the scalar product is for this to make sense. So I'm going to do that right now. I'm going to define a scalar product on that. I'm going to use round brackets, so I'm going to use a slightly strange ket notation, but I hope you don't mind. So this is the scalar product on our Hilbert space, and it's defined to be, got to get this right as well, 1 over G yep. Good. Now we have a scalar product. A sesquilinear form on these vectors. Okay, okay, it's just the normal scalar product, right? You know, okay, I've got the complex conjugation in the second argument, but I could put it in the first argument. And then there's a 1 over g factor here. So you look at this, and you look at that above there. Let's look at these two things. And it's like pretty close, right? So what's the difference between this thing here and that thing here? Well, the difference is there's this t inverse in there. That's a bit annoying. But there's no complex conjugate. But I told you that we're now going to focus on unitary representations. And those are representations which obey that equation. So we can get rid of the t inverse and we get a star instead. And so actually it turns out that these equations here are exactly this inner product. So I'll summarize corollaries 2 and 3 using this notation. It's the same content, just different notation. Okay, you have to remember those corollaries. I'm about to delete them. Let's write out corollaries 2 and 3 in terms of this scalar product notation. And we'll see that we get a quite nice result. So corollary 2 says something like J1, K1, oh, used the wrong notation, sorry, round bracket, so these vectors, remember I invited you to think of R and R1 and R2 as vectors on the group. Doesn't matter which entry of them you're looking at here of the representation, that vector is always orthogonal to that vector there, if those two representations are unequal, right? And if they're equal, then we get that. So there's three, actually we're not dealing with one matrix here, we're kind of dealing with a tensor, a three-dimensional matrix object. So this is something, I'll draw a picture here so that you got at least something to attach your thoughts to. Because there's this Rj1k1 is the J1 k1th matrix element of the unitary representation of the element T. So how are we going to think about that? So I want to give you a picture. Really what we have here is a 3-index object. So it's a matrix. Remember, this is the matrix J, K matrix element of the unitary irrep rho T. But I want to invite you to think of T as a third index, right? It just labels elements of the group. The group has G elements in it. So really you should be thinking of R, J, K, T as a kind of cube of numbers, right? I'll try and draw this. So you think of a cube. I'm trying to draw a cube here. I've got a cube. Now the x and the y directions, this is just the rows and columns, right? So this is labeled by J. This is labeled by K. And the third dimension is labeled by T. And so try and think of this thing here as a bunch of matrices listed one behind the other, or as a cube of numbers, a three-dimensional array of numbers. And so, you know, up here we've got 1, 1 identity. That's the first entry in here. And then as you go back in this dimension, then you've got R1, 1 of whatever element is the last, right? And so on. So you can fill out this cube of numbers, and that's what this thing here is. And all we're doing here is looking at the cube in different directions. If we fix on a given x and y dimension, so to speak, J and K, matrix element, and then we look into the cube, then we get ourselves a vector, right? That's this vector I was speaking about up there. For a fixed J and K, I can go dive into the cube and I get a list of G numbers. That's a vector on the group. And then this is saying that no matter how I dive into this cube, if I pick any two vectors, I'm going to get 0 if the x and y dimensions are unequal, or if I got the same representation, then no matter how I dive into the cube, I'm going to get 0 unless I happen to be on the same coordinate. So I pick two vectors, you know, I dive into the cube here once. This is rj1, k1. I go in here, j2, k2. All these vectors that you select by looking into the cube and then taking the inner product, they're all 0 unless it's the same vector. In which case you get 1 over n. Yep.
What does that word say after matrix?
Element. Sorry. Question was what's that? ELT. Element. ELT. All right, so that's how you're meant to interpret these things. And now what we're going to do is take these. I mean, these are the kind of like defining equations of irreducible representations. And they give us this complete basis of vectors on the group. We're going to take this and apply them now to characters. So I'm going to, if you remember, a character is a trace of a representation. In terms of matrix elements, we can calculate that as r, j, j, t, j equals 1 to the dimension of the representation, which is n. And we can give this a name, we can call this chi of t. So characters, I introduced those a bunch of lectures ago. Characters are just these functions that you define just like that. And now I'm going to finally draw these two subjects together. So if we define a character like that as just the sum over blah, 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 we're going to rewrite again or use corollaries 2 and 3 to derive some consequences about these characters. So, you know, I'm going to use corollaries 2 and 3 to determine something very So corollary 1 straight up tells us that if our characters come from different irreducible representations, this inner product here is always 0. And corollary 3 leads to the consequence that these characters are normalized, and that's it, I think. Yeah, that was it. There's no more consequences to draw. Since it's a character, it's the same character, it's on the same irreducible representation, I don't need to write blah, 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 right? Now, I don't know, I don't think I need to prove this, but I will show you how you might prove. The first one should be obvious, but how might you prove this one? Well, I'm going to do it by just taking this equation and erasing and summing. So the character is what you get when you sum J1 over K1. And I'm going to call this K. So that's what, because everything's linear here, this is a linear function separately of these things here. That's chi and that's chi. And now I have to sum over here. Now what did I do? I summed J1 equals K1. And I summed J2 equals K2. But that's a delta function, right? So J1 has to be the same as K1. K2 has to be the same as J2. I'm actually taking the trace of the identity matrix here. Which is equal to 1, right? So that's how we prove that statement there. So these are the so-called orthogonality relations for characters. Now so far you're like, oh great, you just define some functions on the group, good. We're going to put this result now to work, to actually determine when, to determine how many times an irreducible representation appears as a sub-representation of something else. So let's put these curious observations to work. So far, so nothing. Should have, this is just a reminder of stuff we now already know. So imagine we have some representation of our group G. We just got one, right? We already have some examples. You could take the permutation representation. You could take the regular representation. There's a couple you could try. And we know that any representation you have, doesn't matter how big or small, is always a direct sum of irreducible representations, right? That we did this proof by induction several lectures ago. Now what we're going to do is find a way to count the number of times each irreducible representation appears in this list. All we know up to now is that there is this list of irreducible representations, that some of them appear more than once, or can appear more than once. So you could have a particular irreducible representation appearing 10 times in this list, and then the second one appears 3 times, and so on and so forth. Let's find an actual way to count the number of times an irreducible representation appears in this list. And here's the kind of amazing bit, right? We have an arithmetic way to compute the number of times that an specific irreducible representation appears in this list, using stuff that we can calculate. So we have the representation. That means we can work out the character, right? Remember, the character is just the trace of the row of the T. So if we have the unitary representation, then we can certainly work out the trace of it. And if you have your favorite irreducible representation, I don't know how you found it, that comes later in the story. You have one, and you want to ask, well, does it even appear in this list? Maybe it's not even in this list. Or if it's in this list, maybe it appears many, many times. How many times? Then it turns out you can work out that using exactly this number here. And what is this number? Well, we know, right? This is 1 over G sum T phi of T. So this is that thing there, that number there. It's a complex number, a real number even. Chi T. So this we can compute, we could sum over the elements of the group. So actually we have an equation that we can put on a computer to count the number of times this representation appears in this list. Okay, I wonder if I can even do the proof on one line. Okay, phi is the sum. Well, phi is the trace of the representation. But the trace of a matrix with that block form here, and I should draw a picture for you. You should be thinking that rho looks like this, right? It's in block form. And that's Wj 1, 2, 3 in this case. Yeah? So the trace of rho is equal to the trace of these sub-representations here, rho Wj3. And in here, we have rho Wj1. So the trace of each one of these things is a character as well. Okay, I'm going to input this information into this equation here. But let's look. Yep, it's still there. What can this, each of these are characters of an irreducible representation. What can these numbers be equal to? We only have two possibilities, right? Either this representation here, this row WJL, is not the same as this representation we have in our minds, in which case these characters are orthogonal, and you get 0. Or this is the same representation as that, in which case we get 1. And so we're finished. You know you're onto a good thing when the results are so easy to prove. There's this tendency to evaluate complicated proofs as being better or harder or smarter, right? But I would argue quite the opposite. If you need to make long, complicated, difficult to understand proofs, then you probably have the wrong definitions. The way you should be really doing science is you should be building things up gradually and setting up the best definitions. You should think very hard about defining something before you do it. And the better you make the definition, the more well-crafted the definition is to the objective, the easier the results should be to prove. The results should practically prove themselves. So that's when you know you've built a really good theory. And this applies in maths, of course, right? We're talking primarily mathematical here, but it also applies in physics. There's this tendency when you're investigating complex physical systems to think in a complicated way, to look for complicated explanations. But if you build up your notions cleanly and you try and define what you're interested in a careful way, by testing your ideas against many examples, then the argument should get simple. So what you don't see here, the Metastory, is that people were scrambling around trying to understand these ideas for decades. But as they tested more and more examples, they came up with cleaner and better definitions until we have these kinds of definitions that you see here today. So what you miss in a lecture like this is this whole historical development of the story. People started with group theory. They were scrambling around trying to understand groups, and then they started looking at ad hoc at representations of groups, and they had many examples, and they tried to organize these examples, and they came up with better and better definitions until we landed today with this perfect distillation of optimized definitions to allow us to talk about representation theory. So that's what you miss in a lecture like this, is that kind of mess in the history. And what you see in the research literature when you go to a research field is you see the mess. You see people arguing with long, complicated papers with proofs that are many steps and very complicated and difficult to follow, and people arguing with each other, and definitions being overturned. People will define things one way, and then other people will say, no, this is a stupid way to do it. And this big argument in the literature takes place over years and years, and then slowly things get distilled to the purest essence. And that's what gets presented in an advanced undergraduate course. But the research is always messy. It never looks like this. It's always messy. So I'm not teaching you so much in the form of research skills here, because we have this perfectly composed mathematical structure, But what you will gain is a set of tools that you can use in research, right? Later on you'll encounter symmetries. And you should think, I remember about those characters. So that's the objective of these lectures. All right, so we've proved this theorem. Just by one computation, we now know how many times an irreducible representation appears in that direct sum. All right. Okay. So in the book of Sayre, where this material comes from, he writes, indeed, it does not depend on the decomposition. That's the proof of this corollary here. That's a bit cheeky. Okay. The number of times that this WJL is isomorphic to W doesn't depend on the order of terms in that decomposition up there. The way you can convince yourself of that is to notice that this is a well-defined equation, meaning that the phi doesn't depend on the indices we've used here. So the trace of that character doesn't, if I decided to put that irreducible representation second and the other one first, then I would get the same phi at the end. So the left-hand side equals the right-hand side still, because addition commutes and direct sums, and this is a well-defined function. So that means it doesn't depend on the order. So I hope that's satisfactory for you as an explanation. Sometimes the simplest proofs are the hardest, but this one should be clear. Okay, there's a second corollary. Two representations and this is also, it barely requires a proof. So, but this is amazing, right? This is an amazing result. It tells us that how to work out if two representations are the same or not. Because that is non-obvious. That is super non-obvious, right? So let's just I'll dwell on the non-proof of this for a second, and then the consequences. Two representations of the same character are isomorphic. Why would this be the case? Well, the characters allow you to read off the number of times each irrep occurs in that list, and the list doesn't depend on the order. So up to this reordering of the irreps, we actually know exactly how many times each irreducible representation occurs in that direct sum up there. So the character has that information inside it. And either you have the irreps appearing the same number of times, or you don't. If you have them appearing the same number of times, then they're going to have the same character. And if they don't, then they're different representations. So this is they don't even require proofs almost, these two statements, but they've just given us a power technique to work out if two reps are the same or not. So now here we go, application, right? Let's compare the state of our knowledge at the beginning of this lecture and now where we are at the lecture now. Suppose, and this is not unrealistic, explain what have means in a second. So this could happen to you at any point when you're going through physics now. You have some physical system, a crystal. You have some other physical system, the hydrogen atom. And they both have symmetry groups. And you have some symmetry, or representations of these symmetry groups. What does it mean to have? It means someone gave you the matrices, right? So to every element of the group, you have the matrix elements. You wrote them down. They're a list of complex numbers. And they could come from totally different places, as I said. Like, you could have the hydrogen atom and you could have a crystal. And you have these matrices. And you better make sure that they have the same symmetry group. So whatever symmetry group you have acting on the hydrogen atom, it's going to be some polyhedral group. Better be the same group as what's acting on your crystal. So let's suppose you've got the same group acting on your thing. So you could have totally different physical systems with the same symmetry group. That's, I hope, relatively easy to imagine, right? I'll give you a more concrete example. Suppose you have a cube. There you go, a cube. It's just a little cube system. It's a cubic system. I don't know, there's a particle in it, whatever, right? It's a symmetric cube. It's got some stuff in it. And then what's the symmetry group of a cube? Well, it's the symmetry group of a cube, right? You're allowed to do these permutations and you can rotate this cube around. That's one physical system. And then you might have a lattice on this is system one. Here's a lattice system. It's a cubic lattice system, so it's three-dimensional. Yeah? Try to imagine a three-dimensional grid. And, okay, that's a 3D grid. And then you've got some electrons hopping around on this three-dimensional grid. What symmetries does the three-dimensional grid have? Well, amongst others, it has the same symmetries as that of the particle in the box, right? This is cube. You can do all the things you can do with a cube, you can do on the grid. And then each of those symmetries are symmetries, so there have to be some unitary operators acting on these spaces, on the Hilbert spaces. So there they are. Here's the matrix elements. You could even work them out, right? To every one of the symmetries of the cube, you could work out these matrix elements. There's going to be, these are infinite dimensional systems, so it's a slightly poor example, but it's fine. So here you go. You have these unitary matrices here. There's whatever, 6 of them, I think, for the cube. Does anyone know the order of the symmetries of the cube? It's like 24, 12, or 6. Maybe someone can Google it and then tell me. Maybe it's 8. I think it's a subgroup of the permutation group S. Well, it's certainly a subgroup of the permutation group 12, S12, but I don't know how big the order is. Someone's going to tell me in a minute. So you got these matrix elements here, and there's T equals the identity, up to whatever the order of the group is. And here you go, you've got also some unitary operation that does the cube operations on this lattice, R2. So there's this Hilbert space for this system here. There's the Hilbert space. Every one of these cube rotations is given by some operator on this Hilbert space. It does the symmetry. And here's a Hilbert space H2 here. Each one of these symmetries, yep.
I think it's 24 if you...
It is 24, okay.
If you exclude reflections.
All right, let's see.
Reflections 48.
Okay, I'm kind of... Okay, right. Thanks, that's great. So 24 with no reflections and 48 with reflections. Cool, okay, thanks. And it's non-abelian if I remember correctly, so no reflections, sorry. No reflections is 24, and with reflections is 48. So you've got a physical system, you know how to do these kind of operations on it, on your Hilbert space. They have to be unitaries because it's a symmetry transformation by Wigner's theorem. And then you ask the question, and this mind-boggling question. You say, are these two systems actually equivalent? Are these unitaries actually equivalent? Okay, let's ask the question on another board, because it's like, this question seems impossible to answer when you first hear it. So the story so far, right? We have system 1. The symmetries of the cube is the group G, and system 1 is cubic. It has a Hilbert space, H1, and for every symmetry of the cube, there's a unitary matrix that we were given, that we worked out, because we have a basis, right? We have the matrix elements of this thing. You know, we at least know how to do the unitary rotation around the cube, of the cube thing. And we have system 2. One emerged in chemistry and one emerged in material science. 2 completely different places. But they both have the same, they have completely different Hilbert spaces too. Something else I want to emphasize. But the groups of symmetries are the same. You've worked out a basis for this Hilbert space, you know how the symmetry groups act here, and you get other numbers. This list of numbers here. And now comes the mind-blowing question, like how would you even dare ask this question? But the question is, could it be that the symmetries are represented in exactly the same way, that they're really just the matrix elements here are just the same as these matrix elements somehow in disguise? So the question is, does there exist a map unitary? Does there exist a map, I've overloaded all the symbols, U from H1 to H2, a unitary map such that U row 1, I'm going to go ahead and say I made a mistake here, 2, U, so U goes from 1 to 2, U dagger, so does there exist a unitary, a basis transformation of Hilbert space H1 that shows you that actually in disguise H2 was living inside H1 or vice versa? And furthermore, that these unitaries act the same way. And you're like, this is preposterous, right? Because you have an infinite number of numbers here. How is it possible from all these numbers to find a unitary, so which is also an infinite number of numbers, that equals that list of numbers here? What, you know, how dare you even ask that question? But the answer is incredibly simple. And furthermore, this is basis dependent, right? These matrix elements here depended on whatever crazy basis we chose to do our computations. We chose some Hermite polynomials here, and we chose some whatever Chebyshev polynomials here to do our computation. We chose different bases, different everything. What right do we have to ever ask that question, that are they the same somehow? We would have no hope of getting an answer, except this corollaries up there tell us immediately how to get an answer to that question. You take the trace of the first one, and you ask the question, is it equal to the trace of the second one? Oops, without the, yeah, no, that's correct. Yeah. For all t. Either they're the same or they're different, right? Okay, I'm kind of cheating. You have to know all the irreps, right? This is, but the information, phi 1 and phi 2, these characters, are they the same character or are they a different character? If they're the same, there exists that unitary. If they're different, there does not exist that unitary. So that's like mind-blowing that you can get that much information out of such seemingly arbitrary setups. In a way, we could just sort of finish the course here, because that's kind of like the cool bit. But, you know, it gets even better. This is just the tip of the iceberg of representation theory. That doesn't say that the systems are the same. It just says that these actions of the symmetries are the same, right? The only things that are equivalent are the symmetries and how they act. The systems themselves could be still quite different. Because there's all these other degrees of freedom that are left invariant by the symmetries. Yep?
It's maybe a silly question, but why would you want to know this?
Why? Okay, the question is, why would you... Yeah, I'm very excited. Why would you want to know this? In a way, that's such a big question. I can't give a short and snappy answer, but rather on the basis of examples, right? Okay. So if you had two systems that look different, but you find out that they have parts of them that are the same, then that allows you to import knowledge about one system and apply it to the second system. So that's not really an example, but this is the general principle, actually. So it often happens that you learn a lot of stuff about one system. Like the hydrogen atom is a system we know tremendously lots about. And we would love to take that knowledge and transfer it to a second, more complicated system. So if we found somehow that inside another system there was a kind of copy of the hydrogen atom symmetry group, then all the learnings that we have for the hydrogen atom, we immediately just deploy it to the second system, which might be more complicated. So it's really about transferring knowledge. That's one major application area. Right? If I know a lot about system A but not very much about B, but I can find somehow that the symmetries of A are acting on B, then I can tell you stuff about the system B. And specific examples are like lattice systems, like I've just drawn here. So you might know very much about one particular lattice system, not so much about the second one, but then you find, oh, look, all these symmetries are acting in the same way. That's only one aspect. Like, I don't want to make that sound like that's the only answer to the question. Probably other explanations will occur to me as we keep going on. Also, I just like that it's such an audacious thing. You know, if you were thinking about how to solve this problem just on a computer, suppose you had quite small, suppose your Hilbert space was finite dimensional. And this Hilbert space is finite dimensional. I'll even give you a dimension. Let's say it's 5-dimensional. Then look at the search space. What kind of equations would we have to solve in order to determine if a U existed like that? We'd have to solve 25 equations for each value of t. So I don't know how big the group is, maybe 24, right? So 25 times 24 is, okay, it's doable on a normal computer. But if we now start to look at slightly bigger systems, then the numbers of equations that you have to solve in order to find if that U exists or not explodes. Furthermore, the search space isn't linear, right? So a unitary matrix isn't just a list of n-squared numbers. It's a list of n-squared numbers that obeys this quadratic equation here. So you're searching over roughly 400 equations for a matrix that obeys that extra condition there. So it's non-trivial. If you start doing these things numerically, even for this small examples, 5 dimensions, symmetries of the cube, you quickly run into some pretty tough numerical problems, and it just gets way worse, right? So it just seems so amazing that you could answer this question without having to go through this pain of these massive numerical searches. So basically, the big consequence of this stuff is that the study of representations boils down to the study of characters. Once you know the character, you effectively know the representation. So let's imagine now we have distinct irreducible representations. They're each non-isomorphic. We've got a list of them, and there's the characters right over there. And I should say all distinct irreps of a group. So we have a group in mind, and we somehow now have all the distinct irreducible representations. There's the characters. What does it mean if you have all? It means that every other representation you build change the notation, make that a K. Because you have all irreducible representations, there are none missing on the list, so that every other one you can have is a direct sum of copies of these representations here. So far, so trivial. So V is equivalent always to a number of copies of irreducible representation W1, direct sum with a number of copies of irreducible representation W2. And to explain this notation, that just means W1 direct sum W1 direct sum M1 times. The character of this representation is just the sum of the characters. Furthermore, the orthogonality relation for these characters tells us this result. They're all different, right? They're all distinct irreducible characters, so they're either 0 or 1. In this case, they're 0 unless they're the same. So this gives this identity here for the multiplicity. And so this leads us to the final power result for this lecture today. Namely, we actually have a way now of spotting irreducible representations. So we have a criteria. If we have a bunch of numbers, a bunch of matrix elements for a representation, and we can ask the question, is it irreducible or not? Is it one of these special irreducible ones? How do we work it out? Well, we work out the character, and then we take the inner product of the character with itself. So let's take a look at this content here. The character of any representation is therefore a sum of an integer number of copies of the corresponding characters. If I compute the phi scalar product of this function here, then I get a sum of integers squared. So that's an integer. That's why it's a positive integer. And when can that be an irreducible, corresponding to an irreducible representation? Irreducible means that only one time does something appear in this list. Irreducible means that when I work out this decomposition here, I get 0, 0, 0, 0, 0, except for one W whatever, and the rest 0. Which means that of these integers mj, only one of them is 1 and the rest is 0. And that can only happen, that happens if and only if the phi equals 1. So if you work out the character of your representation and then work out this thing here, then you can tell if the representation is irreducible. Like magic. Like how did that happen? So that's the last result, I think, that we're going to cover on character theory and orthogonality relations. We're going to go into explicit representations, I think, in the next lecture. And a couple of examples, yeah. That's what we're going to next. I'm hoping that we'll get to the point where we can construct these representations, giving the characters. So, you know, I made this statement that the study of characters is all you need to know to construct the irreps. Well, then in principle, we should be able to construct these irreducible representations from these character functions. So that's an interesting construction that we should look at. But I think we'll stop here for today and move on to that next time. Thank you very much.